Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games, and today it's time for the big one. Today we're going to figure out if two triangles intersect. So this is going to be a bit of an ordeal. There's a couple ways that you can test triangles for intersection. You may have actually seen one of them before. This on the screen right now is some very old, and by very old I mean it's from like 1997. It's not super old as far as the world as computers go. Anyway, this is an algorithm developed for triangle-triangle collisions by one Thomas Moeller. You may have seen it floating around the internet before. This is valid. It'll work if you want. You can convert this to GML. You'll need to use some tricks to convert very macro-heavy C code to GML, but you can do it if you want. I am not going to do this. I am going to instead use a combination of a couple different tricks to test for triangle intersections. Right off the bat, I'll say that it should be possible to just use the regular separated axis theorem to do two triangle intersections, but I unfortunately was not able to get that working. That's actually the main reason that I was a little bit late posting some of these collision videos, was because I was trying to figure that out. I actually wrote to the author of the book for advice on straightening that out, but unfortunately I did not hear a response in time for this video. So instead I'm going to rely on a few different tricks to figure out if two triangles are intersecting. So let's start in call triangle, and we're going to call triangle's check triangle method.
Hey.
So I said that we were going to be relying on a few different tricks to do this, and the first thing that I'm going to do to check to see if two triangles are overlapping is I'm going to get the planes of both triangles and see if all 3 points of one triangle or the other are on the same side of either of those planes. So let's get down to business. First, var plane A, I'm going to call this is going to equal self.getPlane. The second one, var plane B, is going to be triangle.getPlane. Next, we're going to use the plane equation that we wrote out a few videos ago to figure out a dot product-esque value that is going to give us some information on where each of the points of each of these triangles are relative to the planes. Let me call that P. Var PAA is going to be plane A dot plane equation, and the input point is going to be triangle.A. So this is going to be the plane of our self. I guess I could call this plane self if I wanted to make it a little bit more clear. But the plane of our self, plane equation against the other triangles A. Next, PAB and PAC are going to be plane equations for triangle.B and triangle.C. Next, after that, we're going to do this the other way around. So plane B, PBA is going to be plane B dot plane equation of our self dot A, B, and C. In this, just basically reversing the order of the triangles. And if all of the points of triangle A are on the same side of plane A, then there is no intersection between the triangles because the points are all on the same side of the plane. There is no crossover. If all 3 of the points of our own triangle are on the same side of plane B, same deal. You do need to test both of these because it is possible to have, for example, the points of triangle A on different sides of the plane of triangle B, but the reverse not being true. So you could go about doing this the long way. You could say if sine PAA equals sine PAB, and PAA is not equal to 0, and sine PAA equals sine PAC, then you could just return false, and then you could do this for vertices, and then you could do this for the other 3 vertices as well. You do need to check to see if the results of these plane equations are not equal to 0. Because if all three of the points lie on the plane, that means the 2 triangles are co-planar, and you have to do something else to check if they intersect or not. However, this is a bit of a long and unwieldy line of code, so instead I'm going to first check if PAA multiplied by PAB is greater than 0, and PAA multiplied by PAC is greater than 0. And that is going to accomplish the same thing, but it's going to be a little bit less code. So when you multiply these together, if they have the same sign, then the result is going to be positive. If they have different signs, the result is going to be negative. And if they're both 0, then the result is going to be 0. So this accomplishes the same thing, but it's somewhat more efficient, and it's somewhat less code, and it's somewhat easier to read, I think. And then we can do this same thing again for PBA, PBB, PBA, and PBC. So again, we are going to check if the other set of 3 points are on the same side of the plane, of the other plane. And failing all this, we are going to return true. And there's going to be more that we're going to do between line 427 and 429 to work out some extra special cases where this may or may not be an intersection that we are not detecting here. But if I were to run the game now, then we are going to see that this should include a number of scenarios. You can see that we do indeed have a collision here, but it is correctly detected. If I were to move one triangle into a certain specific location, you can see that we are detecting false positives. These triangles are not actually intersecting, but the game currently thinks that they are because the 3 points of both triangles happen to be on different sides of the plane of the other triangle, even though there's no actual intersection. If I were to move one up or down, you can see that collision is no longer being detected side to side. And this is generally working in a lot of cases. I did write in a little bit of code to these demos to, let's see, to allow me to generate 2 triangles that are on the same plane. And in this case, right now, currently, any arrangement of these triangles, no matter where they are, will result in a false positive because the signs of these plane equations are all going to be 0. None of these returns are going to happen, and then we're just going to skip to the end. We're going to return true. This is actually the heart of the problem that I was having getting this working with the separated axis theorem, was that co-planar triangles were returning false positives under a lot of situations. I was unfortunately not able to get rid of all edge cases under those conditions, and we're just going to have to do this a different way. I was hoping that wasn't going to be a problem because the SIT is indeed a rather useful solution in a lot of cases, but was not meant to be, apparently. So I'm going to close the game. I'm going to open up GitHub Desktop. I think I'm going to... Let's commit some of these changes first. This was just a little update to the test. Ruling out collisions between triangles using the plane equation. If both of these triangles do happen to lie on the same plane, I'm going to, if... I'm just going to return true here for now, and I will come back to this later. Figuring out if both triangles lie on the same plane, you can do this the long way. You can say PAA equals 0 and PAB equals 0 and so on and so forth. You could also just compare the planes. You could see if the 2 planes of the 2 triangles are the same. You could say if plane A dot distance equals plane B dot distance, and the absolute value of plane A dot normal dot dot product against plane B dot normal. If this whole thing equals 1, because in this case, if the planes are one-sided, so you could have 2 planes that are visibly occupying the same space, but they will have opposite normals, and you can compare the normals to each other using the dot product. And if that dot product is 1 or -1, and if you take the absolute value of that, if the absolute value of that dot product is +1, that means that the planes are in roughly the same place. We're just going to return true, and we will deal with this later. Next, we're going to use the separated axis theorem, the good old separated axis theorem for a little bit. We are going to, let's see, let me define var, and in a couple places in this code elsewhere, I think I've called these values something like, yeah, down here. Diff AB is going to be self.b.sub self.a and that sort of notation, but let's go with BC and CA, and this can be C sub B and A sub C, like this. I would call these variables diff AB, diff BC, and so on, except I'm going to need these for both triangles, and I want to make the names a little bit less confusing. So let's call it self AB, self BC, self CA. And For the other triangle, for the incoming triangle, it can be other AB, other BC, other CA. Triangle dot B dot sub triangle dot A, and so on and so forth. And these are essentially representing the edges of each triangle. I really should comment this code, shouldn't I? I'll comment this code before I push it to GitHub. Next, we're going to do a little separating axis test, and I'm going to say var axes is going to equal an array, and we are going to be dealing with, I believe, more axes than we were with some of the other ones. For example, ab triangle. Oh no, ab triangle also used a lot of axes. All right, that's fine. Anyway, we're going to be using 11 axes here. First is going to be self.normal. I suppose it might be a good idea to normalize this. You can also say, actually, is when our normals are calculated. This is not a variable, is it? Yeah, this is a method call for get normal. Okay, that helps a little bit. The first axis is going to be our own normal. The second axis is going to be triangle.get normal. So that is the normal of the other triangle. And the other 9 axes are going to be, for example, other AB dot cross self AB, and then other BC dot cross self AB, and then other CA dot cross self AB, and then you can see where this is going. We're going to cross each of the edges of one triangle against each of the edges of the other triangle. So this can be, I'm going to separate this into like sections. Other AB cross self AB, other BC cross self AB, other CA cross self AB, other AB cross self BC, other BC cross self BC, other CA cross self BC, and then the last one is going to be the same 3 edges crossed against self CA. For a quick sanity check, on the left we're going to have other AB, other BC, other CA, other AB, BC, CA, AB, BB, BC, CA, and on the right we are going to have AB, 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 BC, 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 CA, CA, CA. Just for a quick sanity check to make sure that you didn't duplicate any of those axes or otherwise mistype them. And from here, we can just run the regular, good old-fashioned separated axis theorem. So we're going to say var I equals 0, I is less than 11, I plus plus. If not, call overlap axis, and shape 1 is going to be self, shape 2 is going to be triangle, and the axis is going to be axes index I. So if there is an axis of separation between ourself, the other triangle, on any one of these axes, we are going to return false. Otherwise, return true. And again, we are currently not accounting for the special case where the 2 triangles are coplanar. We're going to deal with that soon. So now, if I were to run the game, and if I were to attempt to generate one of those little edge cases where the 3 triangles, 3 vertices rather, of each triangle are on different sides, that's actually an intersection there, isn't it? Different sides of each other. Okay, here we go. So if we have a case where all 3 of the vertices of one triangle are on opposite sides of the plane of the other, if I can get them all in view at once, that'll be helpful. We no longer have a false positive being reported here. However, if I were to move them into each other, we now do have an intersection being detected. However, if I were to again go back to the special case where these triangles are coplanar, we still do have false positives. That is going to be the subject of what we're going to deal with next. All right. You know what? I'm going to comment this before I commit. Okay, I've written some comments. Phase 1 is going to be testing if each of the points of each triangle are on the same side of the plane of the other. Phase 2 is what we're going to do next. This is when triangles are coplanar. Phase 3 is the regular old separated axis theorem. And now it's time to do some math. So, in turn, there's going to be a couple different tests that we're going to do to see if 2 coplanar triangles are colliding with each other. One of them is going to be simply checking to see if a set of points, if each of the points of one triangle are inside another. We already know that the points are on the same plane. There's a few different ways that we can do this. We can use the barycentric coordinates from not too long ago. I think for the sake of simplicity, and this is not going to be completely optimal code, none of this is really, but for the sake of simplicity, I can say if new call point containing self.a.check triangle, the incoming triangle. So if if point A on our own triangle is within the incoming triangle, then we can return true. We can do this for the other 5 points in this equation. So if call point self.a, self.b, self.c check triangle against the incoming triangle, we can do this the other way around. So if the points of the incoming triangle are inside of our self, then we can also return true. And if none of those happens, we can return false. This is not the end of the story. The end of the story, this is going to account for most cases of triangle-triangle collision, but unfortunately the last one is going to be a little bit more work. Let me zoom in. Let me create 2 triangles that are co-planar. We have shapes overlapping here, but if I move the one away, we no longer have an intersection. So let's see. There are still edge cases. Let me see if I can work out another edge case. It is possible, and you can visualize this in your mind. It is possible to have 2 triangles intersecting that do not have any 2 points within each other. And if I were to attempt to generate a triangle that does that, here we have one. You can see these 2 triangles are coplanar. They should be detecting an intersection, but they are not. If I were to move one so that we have one of the corners inside the other, here we have an intersection. If I were to move it away, we do not. We are detecting a false negative here. And this is the final special case for detecting triangle collisions that I need to test. So the core of the problem that we need to solve from here on out is figuring out if 2 line segments intersect each other, because if none of the points of one triangle if 2 triangles are coplanar and none of the points of either triangle are within the other, then you know that 2 of the edges have to intersect somewhere. And there's a part of me that wishes that I'd implemented down in the collision line class, if I'd implemented collisions between lines and other lines, but I have not. And honestly, this is an easier problem to solve in 2 dimensions anyway, or at least I think it is. So that's what we're going to do. First, we need to project each of the triangles onto a 2D plane so that we can turn these into 2D triangles. This is not going to just be like the XY plane or the XZ plane or the YZ plane or anything like that, because these triangles could be oriented any which way. So instead I'm going to go into the collision stuff, into the collision helper code file. And is this where, okay, yeah, this is collision helper. This is where I'm looking for. I'm going to define a few more helper functions. One is going to be function, let's call it call project onto plane. This is going to take 4 arguments. The first argument is going to be a vertex. The second argument is going to be an origin. The third argument is going to be, I'm sorry, this is going to take 5 arguments. Normal, E1, and E2. I am just going to read through this code as quickly as possible because I want to get through it. I'm going to first define var. Let's call it S is going to be norm dot vertex dot subtract. And that's just sub, not actually spelling out subtract origin. This is not going to be a long function, but I'm just going to go through it quickly so that we can so that I don't have to spend a great deal of time on it. First, I'm going to define var t1 is going to be let's say e1 edge1 dot against vertex dot sub the origin. The next line is going to be var t2 is going to be e2 dot, and it's going to be the same thing, subtracting the vertex from the origin. If you want to save a couple computer operations, you can do this once, save it to a variable. That's just a general rule for a lot of the codes that I've written in this 3D collision series. And then finally, return new vector 3. composed of t1, t2, and 0. This could be a vector too, but I do not have a class for a two-dimensional vector anywhere in this project, so I'm just going to be going with a vector 3 with a z-coordinate of 0, because we are going to be, by and large, disregarding that. Okay, so we're going to come back to that. This is call shapes. This is where I want to be. So before I make use of the function that I just defined regarding projecting a vertex onto a plane, let us first define a few more values. First, var origin is going to be I'm just going to arbitrarily make this self.a. Not arbitrarily, but it can be any of the points on the on our own triangle here, and the rest of this is just going to be defined in relation to the origin self.a. Next, var norm equals self.get normal. You may note that self.get normal has been calculated a couple of times. Actually, has it? Oh, it's calculated farther down. You may wish to define some common terms, such as getting the normal of this triangle, and just like stick them at the top of this method call. If you want, same thing for the edges down here, like self AB, self BC, self CA. I'm not going to do that. I don't want to write minimalist code. I want to write legible code. And in any case, this up here, inside the two coplanar triangle checks, and this down here in the SAT check is never going to run in the same method call anyway, because they're in separate branches. Regardless, next, let's say var e1 is going to be self.b.sub self.a. Again, that is the same value that's down here. If you wanted to, you could call this like self e1, self e2, self 3 e3, other e1, other e2, other e3. Anyway, and lastly, var e2 is going to be e1 dot cross against the normal. Next, we're going to start projecting each of the vertices of each triangle onto the plane, and we're going to create two new triangles that are composed of those projected points. Let me call it var. I'll call it self projected is going to equal a new call triangle, and we are instantiating a new triangle in here, but it's not going to really be used for a lot. It's just going to be a container for points, really. We're not going to be calling any methods on it. And I'm going to break this over multiple lines, because if I were to do it in one line, it would be rather long. The first vertex A, is going to be call project onto plane. The vertex is going to be self.a. The origin is going to be the origin from here. The normal is going to be the normal from up here. E1 and E2. And the second and third vertices are going to look very much the same. So we're going to project all three of the vertices of our own triangle onto the plane defined by the origin, which is essentially the distance from the world origin, and the normal of the triangle. And next, we are going to var other projected is going to be new call triangle, and it is going to also look rather the same, except instead of projecting our own points onto that plane, we're going to project the points of the incoming triangle onto that plane. So now we have two triangles. They're going to both lie on the xy plane. All three of the z-coordinates of both triangles are going to be 0, because remember, call project onto plane just returns a new vector 3 with the projected vertices and 0 on the z-axis. Projecting vectors onto an axis, by the way, or rather projecting 3D vectors onto a plane, this is code that you might want to reuse for other purposes. Projecting vectors onto a plane is something that you might want to do elsewhere in 3D games, but I don't want to make a huge deal out of it. Just if you're ever doing anything and you see code that looks like this, now you know where it comes from. Anyway, we now have two triangles that are projected onto a 2D plane. And what we have now is simply a problem of figuring out if any pairs of 2D lines intersect. So the way that we're going to do this is I'm going to go back to the helper functions code file. I'm going to define two more functions. One is going to be function call lines intersect. And instead of taking like a line object or anything, I'm just going to take 4 points A, B, C, and D. This might start to look a little bit familiar from geometry class. I'm going to define a third function, which is going to be function call points are counterclockwise. This is going to take 3 arguments, 3 vector 3s, A, B, and C. Really 3 2D vectors, because again, the Z coordinate on each of them is going to be 0. And this might be a little bit counterintuitive. When I came across this code initially, I had to think through it a little bit. We're going to be figuring out if 2D lines intersect by checking to see if they're if all 3 of the points are defined in counterclockwise order. If you remember systems of equations for Algebra 1 in school, you might be thinking of ways to check to see if 2 line segments intersect by solving a linear system of equations and like testing the value to see if the point of intersection is within the range of the actual line segment. But that's going to be even more code than we've already written for this video, and I don't think anybody, including me, wants to sit here for any longer than necessary. So we're just going to write a little bit to figure out if any 3 sets of points are in counterclockwise order from each other. To do that, I'm just going to return c.y minus a.y, the quantity of that, multiplied by b.x minus a.x, the quantity of that. And we're going to test if this expression, we're going to return a Boolean, is this expression less than the quantity of b.y minus a.y multiplied by c.x minus a.x. Close parentheses, that is all for call points are counterclockwise. And in the intersection function, to make a long story short, if you have 2 line segments, let's call them A, B, and C, D. To use every geometry teacher's favorite set of words ever, they're going to intersect if and only if essentially you find an axis of separation between them, as we've been doing for a number of the prior videos with the separated axis theorem. So, and this is going to be a little bit long to type out because of the long function name that I decided to give this one. But our return statement for this function can be a single expression. We're going to return points are counterclockwise. A, what did I say? A, C, and D is not equal to points are counterclockwise B, C, and D. That is going to be one expression. And let me dump this on a second line. Points are counterclockwise A, B, and C is not equal to points are counterclockwise A, B, and D. And that should be our entire expression. All right, parentheses are in the right place. Good. This is a function which will check to see if two-dimensional lines intersect. And now we can hop back over to the check triangles code, and we can actually use this. So both triangles have 3 lines. We have 3 times 3 equals 9 intersections to test. For example, I can say if call call lines intersect self projected dot A self projected dot B is going to be the point of one line segment, and the second line segment is going to be other projected dot A and other projected dot B. If these 2 line segments intersect, return true. There is a collision between these 2 triangles. And now let us do this again for all of the other 8 pairs of line segment intersections. This is going to be a bit like the 3 axes of separation down here, and that we're crossing one into the other, but it's not going to be quite as short as the other code was. I keep typing D instead of A. So again, if you want to do a sanity check, A, B, A, B, A, B, B, C, B, C, B, C, C, A, C, A, C, A on the first line segment, and AB, BC, CA, AB, BC, CA, AB, BC, CA on the second line segment.
Hey.
And if none of these nine functions return true, then we can prove that these two triangles do not intersect. So I'm going to run this hopefully for the last time. I am going to generate two sets of triangles that are lying on the same plane, and let's see if I can generate one of those like edge cases here. I can. Okay, barely. You can see these triangles are on the same plane and they are intersecting without any of the points being contained within the other. And collisions are correctly being detected here. If I were to move outside of the plane, we can see that we no longer have collisions being detected against each other. That is great. And if I were to generate any other two triangles, we should be able to see that any and all edge cases will be accounted for. If I have one that's coplanar with the XY plane and another that's not, we have collision correctly being detected. Okay, and so on and so forth. So this is a lot of code, and as you probably summarized from this video, this is not very efficient. Checking to see if two triangles intersect each other is actually something that you really do not want to do very often, because it is expensive. If you're thinking back to the Thomas Moeller version of triangle-triangle intersection, that is slightly more efficient, although it's still a lot of math, so it'll still be fairly slow. You can actually work out elements of the code that are similar between these two methods. For example, checking the plane equations to see if all three of the points lie on one side versus the other. He does a slightly different, well, really a very different way of checking to see if the like the intervals of the two triangles overlap on any axis. But that is slightly more efficient code. It's just like if I were to try to read that, and if I were to try to do that on the video, it would be about as much fun as me reading from a phone book. And the point of these videos is for me to explain how it works as best as I can, so I kind of opted not to do that. I was originally hesitant as to whether or not I wanted to include triangle versus triangle intersections in this series to begin with, because it is so slow, and generally if you have two 3D meshes, you're going to be dealing with hundreds, if not thousands, of triangles that you're checking against each other. And there are ways that you can optimize that, but it's still generally a very slow process and not something you really want to do if you can get away with it. When we get to checking 3D meshes for collision, you're going to see how unpleasant triangle collision detection becomes very quickly. And also, actually, I can run this into bug mode, and I can run this through the profiler. Yes, please. If I were to open up the profiler, where is that? Others, that's buffers. Debugger, Windows, profile. Oh, it's over here. And if I were to look at how long, for example, the point and check points take, and we can move these around. And if I were to stop profiling, it is this function call here. A single function call for checkpoint is costing, that's 2 microseconds, which is pretty fast. If I were to instead check, for example, maybe a sphere versus an ab. Let's see, so that's an ab and an ab. I was thinking a sphere and an ab, like this. And if I were to run the profiler on this instead, and I'm going to let that go for a couple of seconds, this is taking 15 microseconds instead of, which is a little bit more time than point and point, but ab and sphere, it's still pretty fast. 15 microseconds, you can get away with doing this hundreds of times per frame, and you'll be fine as far as performance goes. However, if I were to change this to what is triangle? Triangle and triangle. We can run the profiler on this, and this is going to be a lot more costly than any of those other 3D collision tests. I'm gonna let this run for a couple more seconds, and you can see that this is taking up almost a quarter of a millisecond, 250 microseconds plus every time for a single function call. It is a lot more math. A lot more lines of code are running in triangle than in, for example, sphere ab, which is really just checking to see the distance between 2 points is less than or equal to the radius. And this is something that will not scale nearly as well as collisions between primitive shapes. Collisions between primitive shapes are very nice performance-wise. When it comes to 3D collision checking, collisions between triangles are not.
Hey.
Let me test ab versus ab. That's not an ab. Ab versus ab. Whether or not they actually intersect is a little bit secondary as far as performance is concerned, because I'm more interested in like the average case. But I guess if I really wanted to test the average case, I would be like moving these shapes around in different ways. Ab takes about as much time as ab sphere did. Regardless, triangle collision is here, and you can choose to use this if you want. I am going to commit this last code to GitHub. And again, there are more efficient ways to do triangle intersection, but any way you do it is still going to be a lot more costly than the other collision detection algorithms, just because it's going to be a lot more math happening. Maybe instead of being like 16 times slower than ab, some versions, maybe Thomas Muller's version of triangle might be just like 8 times slower. Either way, it's still less than ideal. So let me close the debugger. Next time I want to do something easy, I'm going to start assembling triangles into 3D models, and I'm not going to be getting into optimizing 3D models using things like octree hierarchies and that sort of thing. But I will be setting up some 3D models that we can test triangle collisions with in bulk. I'm going to be importing some 3D models into the game, or into the test program. I keep calling it a game, and we're going to be creating a model data structure. Until then, I hope you all found this useful. If you want the code for this, look for the GitHub repository down in the video description. I try to post about 2 game dev videos a week, one tutorial like this, and one Let's Make a Tower Defense game, which is almost done. There's like 3 videos left in that series. I have a Patreon, so if you want to contribute towards any of these videos being made, look for the links to that in all the usual places. You could see some fun things like your name in the credits, or a shout out at the end, verbally, on the end screen. So if you wanted to pledge, I would definitely appreciate it. Otherwise, I hope you all found this useful, and I will see you all later. Special thanks to Edward Holt, Emily Koyo, Gunnar Clovis, Posha, Sindra Larson, Squarecrow, Tusk, and Zenjament for supporting these videos. If you want to see your name in the credits or hear yourself shouted out at the end like this, head on over to the Patreon page down in the video description to join the fun.